No, no. It's basically today and then maybe one more time in the next semester. But we're always going to be at 7:01.
And next Friday is in person.
Yeah. 7:01. Yes. Oh, lots of people are joining. Good thing that we waited.
See, any kind of course.
All right, so I think we can get started. So today we're happy to have Abhijit Krishnam from MIT. He's a fifth-year graduate student working with Max Matlitsky, interested in problems related to boundary criticality. And today he's going to tell us about a new approach to the Kondo impurity. So thank you.
Yeah, thank you for the introduction. Sorry about that. All right, yeah, thank you for the introduction. I'm Abhijit. Today I'll be talking about Kondo impurity. Thank you for having me at the seminar. This is work I've done in collaboration with my advisor, Max, and it is on the archive already. And so if you want to scan the QR code in the bottom left, you can access the paper, or you can just look up the paper. It's the same title as the talk. All right, so first, let me start off by giving a brief overview of the single impurity Kondo problem. For those of you who don't know, the single impurity Kondo problem is a problem where you have a magnetic moment in a metal. So we have a free electron gas with K flavors or channels of electrons, and we have a spin S impurity sitting at the origin of the metal. It interacts with the rest of the metal with a delta function interaction, and there's been a lot of interest over the years in trying to figure out how the properties of the metals change in the presence of this impurity. It has been used to develop new theoretical methods in physics. It was first studied with perturbation theory by Kondo in 1964. Later, Wilson used numerical RG, numerical renormalization group, to characterize the behavior numerically for all values of the Kondo coupling J. And finally, one of the more recent developments relatively is the exact solution by beta ansatz, by Nut and Andre, Paul Wiegman, and others. There's also been experimental work on the Kondo problem. It was first observed in the 1930s by De Haas in gold wires. Here, we have a plot of resistance versus temperature. And at very low temperatures, we see that the resistance decreases as a function of temperature. And then at the crossover temperature of about 4 Kelvin, the impurity contribution is less important and the phonon contribution starts to become more important. Additionally, there is screening of the impurity. There is the underscreen regime, which occurs when the number of channels K is less than 2s. This occurs because there are not enough channels to completely screen the impurity. And for K bigger than 2s, there's the overscreen regime, where at strong coupling, each channel partially screens the impurity. And so this screening has been measured experimentally. Here is a plot of the impurity magnetization as a function of external magnetic field. At very low temperatures, the magnetic field acts as an IR regulator for the problem. And so for a large magnetic field, the impurity is not screened at all. You can see the impurity magnetization is close to a half. And at much lower magnetic fields, the impurity gets screened to having a magnetization of 0. And one more direct measurement of this screening of the impurity is measurements of the Kondo screening cloud. This here is an experiment done in 2020, where the Kondo model is placed in a box of length L. And now we have two IR scales at play here, the temperature and the length of the box. And this group measured the effective Kondo temperature as a function of the length of the box. And they found that the amplitudes of the oscillations of the effective Kondo temperature were large for small values of L. And then once L exceeded the infinite length Kondo temperature, then the oscillations went to 0. So there's definitely some very interesting physics here that's been discussed theoretically in the late 1900s, and more recent experimental results verifying some of those theoretical predictions. The classic way the Kondo problem studied is through a reduction to a 1D problem. So here, we're going to assume that our Fermi surface for our electron gas is uniform and spherical, and we'll also assume S-wave scattering off the impurity. In this case, each incoming electron wave contributes equally to each outgoing electron wave. And so we can group incoming and outgoing waves near the Fermi surface with the same energy and label them as left and right movers, respectively. So we end up getting a folded action for left and right movers on the half line with Fermi velocity Bf. And then we also have, they mix with due to the interaction with the impurity at the origin. Alternatively, we can unfold the action, set psi r of x equal to psi l of minus x, and then we get just the left mover or just the right mover living on the full real line. So now I'll just go into a brief discussion of the qualitative phase diagram and RG flow of the problem before going into our work more specifically. So there's only one parameter here. There's the Kondo coupling J. For J equals 0, we're at the weak coupling fixed point. When J is less than 0, we flow back to the weak coupling fixed point. At large RG scales, the impurity looks as if it's not coupled to the metal at all. Whereas if we go to antiferromagnetic coupling, we flow to a strong coupling fixed point, and at large scales, the impurity looks like it's being screened by all of the channel's electrons. This weak coupling fixed point was first accessed by perturbation theory in J by Kondo, and the following beta function describes the behavior of the RG flow near the weak coupling fixed point. And so you can see that for small positive values of J, the coupling just runs off to infinity. We can also understand the strong coupling fixed point qualitatively by considering the following toy model. Let's reduce this problem to a tight binding model where we have discrete sites running from 0 to infinity, and we have some hopping term between the sites, and then we have our usual Kondo interaction. The Kondo interaction effectively looks like just the total spin squared at the impurity site. And so for J large, we want to minimize this term. And the result of that is that the K electrons screen the impurity spin from S to S minus K over 2. The remaining electrons can't enter the impurity site. That would violate Pauli exclusion, or it will increase the total spin. And thus, the remaining electrons see a hard wall of the impurity. In other words, there is a phase shift of pi at the impurity. This strong coupling fixed point can be characterized with boundary conformal field theory. This was done by Ian Affleck, Andreas Ludwig, and others. And you can get the low temperature behavior of observables at the strong coupling fixed point by looking at the first relevant operator at strong coupling. The intermediate scales of the problem have been captured numerically by beta ansatz. So the beta ansatz solution produces the thermodynamic behavior of the system at all energy scales. And these results are in agreement with the weak coupling and strong coupling results I mentioned earlier. And so we have a numerical understanding of the intermediate scales, but an analytic understanding, a qualitative understanding of the intermediate scales are both currently lacking. So far, my discussion has been limited to the underscreen regime. I'll also mention the overscreen regime, which will come up later in the talk as well. Now the impurity spin of magnitude S is screened to 0 at the overscreen fixed point. Each channel partially screens the impurity spin. This fixed point, also a non-Fermi liquid fixed point, has been characterized by boundary conformal field theory techniques by Ian Affleck and Andreas Ludwig. And also, Vedant has computed observables at intermediate scales in the same way that it did for the underscreen regime. So this has basically been where the field has been at for the last 20 to 30 years. There hasn't really been as many new developments in understanding the Kondo problem since then. Recently, however, there have been developments in boundary conformal field theory that show promise for understanding the Kondo problem. To refresh people's memory, boundary conformal field theory is a study of the boundaries of systems with conformally invariant bulks. And that indeed is a description of the Kondo problem, because the 1D free electron gas is a CFT. These modern techniques have led us to discover new universality classes on the boundaries and defects of the ON model. And additionally, it's already been used for large spin S impurities in ON models for calculating quantities such as the anomalous dimension of the spin. So the goal of this work is to use some of those same techniques to study the Kondo problem. And our approach will be to expand in 1 over S. And hopefully we'll be able to capture all scales analytically for large S with these techniques. Our strategy is threefold. We'll first consider the infinite spin limit, where the impurity spin direction is frozen. We'll take S to be large and finite. There we'll restore the SU2 symmetry order by order in 1 over S. And finally, we'll compute the RG flow induced by the spin fluctuations. Then with the RG flow, we're able to compute thermodynamic observables, which we can compare with beta ansatz. We also can compute observables difficult to calculate with beta ansatz because we have access to the correlation functions in the theory. This includes transport properties such as the impurity spectral function and the finite temperature resistivity, and also the Kondo screening cloud profile. I'll note that our treatment of the multi-channel double scaling limit, take S to infinity with K over S fixed, is similar to work done by Haoyu Hu and Chumiao Si in 2022, where they considered a Bose-Fermi Kondo problem. So first, let's consider what happens for infinite S. And I'll note that we first will show K equals 1 for convenience, and then we'll talk about the overscreened regime. All right, so for infinite S, we'll take S to infinity and we'll keep Sj fixed. And we first will find that the spin action suppresses all fluctuations. And so the spin is effectively frozen. Without loss of generality, we'll take the direction of the frozen spin to be the positive Z direction. In this case, the up spins will see a positive delta function at the origin, and the right spins will, and the down spins will see a negative delta function at the origin. This delta function will induce a phase shift rho between the right and left movers. For small j, rho goes as Sj over 2. And for large j, rho goes as pi, which is what we'd expect from our earlier analysis of the strong coupling fixed point. At large j, we expect the electron to see a hard wall. And this encodes exactly what I mean by the phase shift. The right movers are shifted by a phase compared to the left movers. That flip sign based on whether the spin is up or down. Once we do this, we get the following infinite S action for the problem. We just have free left movers and free right movers living on the half real line, and the correlation functions between right and left movers are related by this phase shift. Additionally, we can ask what are the marginal boundary operators that live at the origin for infinite S, and these will end up playing a role for us when we write down our effective action at finite S. The first marginal boundary operator is psi r dagger sigma 3 psi r, and this just tunes the phase shift of the action between rho equals 0 and rho equals pi. The second boundary operator that will be important is psi r dagger sigma I psi r, and this tilts the boundary impurity spin, and it forms a vector under the remaining U1 symmetry when we broke our SU2 to U1. And finally, there's psi r dagger psi r. This breaks particle hole symmetry, and we won't consider it in our later analysis. All right, so that is our understanding of the infinite S limit. Now let's take S to be large and finite, and let's restore the SU2 symmetry order by order in 1 over S. So when S is large but finite, now S frozen plus SB breaks the SU2 symmetry because the spin is allowed to fluctuate. And so we can add terms back to our action, order by order in 1 over S, to restore the SU2 symmetry. We can add terms that describe the interactions between the spin and the boundary operators. And we can also add boundary contact forms. These are the two terms we're allowed to add to restore the SU2 symmetry. First, I'll briefly go over the spin action again. It's given by the usual Berry phase action. And we'll write the spin order parameter n in terms of the Goldstone modes pi1 and pi2 for convenience.
Can I ask a quick question? So
Yeah.
If at S equals infinity, you've broken SU2 symmetry, how do you perturbatively restore it?
Right. So
or are you doing something non
yeah, I guess this is kind of what I'm going to be going to in this slide. We'll ask ourselves at finite S, what happens when we tilt the impurity spin? And if our theory is indeed SU2 symmetric, the action shouldn't change. And then we can ask what terms we need to add back to our action to restore SU2 symmetry. Does that answer your question?
Are you doing a like a Taylor series expansion or something like that about the S equals infinity limit, or are you just
So
you're not doing a Taylor series expansion about S equals infinity?
I mean, effectively, it ends up being an expansion in pi because pi effectively goes as 1 over square root S. So in that sense, it's an expansion, but we're not doing it as a Taylor expansion. We're saying let's
summing
shift
series all the way out to infinity somehow. You've got an infinite number of like terms.
Yeah, so if you look here, which I'll get to, there will be an order pi term that we have to add, an order pi squared term, an order pi cubed term, and so on and so forth. And then to subleading order in 1 over S, only the first two terms will end up impacting our calculation.
All right, please continue.
Okay. Yeah, so as I was talking about, we can ask what happens if we rotate our system by some angle theta and use that to figure out what the interaction term would be. So under an SU2 rotation, psi transforms this way, and our order parameter n also transforms in this manner. And so to write down what happens to the frozen action under this SU2 transformation, we can express it in terms of the current by Noether's theorem. And so we find that delta S frozen is given by minus theta I ji integrated along all time. And then to compensate for this change in delta S frozen, we have to add this interaction term epsilon ij pi I jj. And the next terms in our expansion, we can't get from this nice picture with the SU2 current, but we can get it just by asking ourselves what happens to the frozen action if we rotate the impurity spin, and what terms we need to add back to our action to restore the SU2 symmetry. So these are some of the terms that we have to add back to our action. We also have to add contact terms at the impurity site to fully restore SU2 symmetry. So there are two contact terms we have to add for zero magnetic field. The first term is this delta m pi squared. And this term we must add because we have to require that the effective potential for pi is 0. There's no preferred value of pi. And this ends up being regularization dependent. The other term we have to add is a correction to our Berry phase term. And this term's a little subtle. We can calculate it as follows. Let's put our Kondo system on a finite size system, and let's require these boundary conditions for our fermions. For this set of boundary conditions, the system is gapped for all values of our phase shift rho. And so we can integrate out our fermions and find this expression for the interaction terms in terms of just the pi fields. We see that the effective action for pi has a fractional value of the Berry phase term. And so we must add a correction term to restore quantization of the Berry phase. And you'll notice that at rho equals pi, this correction term is equal to -1/2, which is what we'd expect for an impurity spin being screened from S to S -1/2. In the presence of a magnetic field, we also have to add another contact term. This we compute in a similar way. We put it on a system with these boundary conditions, a hard wall at L and our usual phase shift at 0. And for this system, the electronic spin density in the z direction is rho over 2 pi L. And because the total spin of the system must be quantized, there must be a correction of minus rho over 2 pi at the impurity site. And this effectively is a Friedel sum rule that you may have learned in solid state physics. So we end up with this effective action for the Kondo problem for k equals 1 and large S. We have the frozen action with the Berry phase term. We have these interaction terms, these contact terms. And if we want to consider non-zero magnetic field, we add an additional contact term. All right, so now that we have our effective action, we can compute the RG flow just by using Wilsonian RG. So if delta L is our is a small change in our RG scale, we find that the interaction term in our action gets modified by sine squared rho over pi s times this term over here. If you remember from earlier, this term is exactly what tunes the phase shift, and so we find out that delta rho is equal to this quantity. Then we end up getting this sine squared rho over pi s is our beta function. We can compute rho's dependence on the RG scale, which is this expression, and for an IR cutoff T, rho has a following dependence on temperature. And here I'll mention T naught is just a dynamically generated temperature scale, which is convenient for us to use later on. So I guess that was the math, but here's what this RG flow looks like. There's a flow from 0 to pi. At the weak coupling fixed point, we recover the perturbation theory result from Kondo. And at the strong coupling fixed point, we have the effective ferromagnetic coupling to a spin of magnitude s minus a half. So that's k equals 1. Now we can go to the multi-channel case where k is on the order of s.
A quick question before you move on.
Yeah.
So, yeah, a lot of these are going by pretty quickly for me, but like, what approximations have you made?
We have the only approximation we've made is that s is large.
Okay.
So it's non-perturbative. Our expression is non-perturbative in rho. It's only perturbative in 1 over s.
Is this a common setting in an experiment?
I would not say it's a common setting in experiment. I think the value is more in enhancing our understanding of this problem.
So there are like no large spin impurities in materials? Is that?
I think you can create an impurity quantum dot that has an effective spin of greater than a half. I think most of the experiments have been done so far with s equals a half. But in theory, you could do an experiment with a quantum dot of s greater than a half by using Hund's rule to align the orbitals in the quantum dot.
I was just referring to like a metal, not a quantum dot. Can't there be spin impurities with like spin 5 halves?
There are.
Right?
There are like 3 halves, 5 halves.
3 halves, 5 halves. So then you should be able to compare to experiment.
I'm not aware of any experimental results on 3 halves and 5 halves. I would be very interested in hearing about it.
So I guess the situation is you just have a metal with a spin 3 halves or 5 halves or 4, or various atoms can have some spin. And so typically there'll be various spinful impurities in a metal. And so it might be interesting to track down some experiments where they've deliberately, controlled the population of a certain kind of spin impurity.
Yeah, I haven't found any experiments when I was looking for it, but if there are experiments, I would definitely be interested in comparing to those.
Okay, and then maybe my question is, what would you expect to see in such an experiment? Like, what would be different?
So I think,
Do you know?
sorry, what would be different from s equals a half?
Yeah. Let's say.
So the difference between s equals a half and s bigger than a half is that at very low temperatures, you still have a remnant impurity spin in the single channel case. And so like for example, you'll still get a diverging susceptibility. You'll still have the usual temperature dependencies of the specific heat. for low temperatures. But you'll still get the resistance signature. And in theory, if you can do the right experiment, you should still be able to see a Kondo screening cloud.
And these are things that come out of your theory that haven't been described before, or is that
I think so. There's the beta ansatz has given numerical answers to these to some of these quantities, not all of them. And this is more of a theoretical way of understanding what's physically going on at intermediate energy scales.
So should we take
So-
seriously its coupling to S minus 1/2 when S is close to 1/2? No, right? We shouldn't think about it as vanishing when S is 1/2.
Well, so as I'll explain in a little later. Our results can't capture what happens when K is equal to exactly 2S. The 1/S expansion breaks down. And so we won't get a handle if on situations where the number of channels is exactly equal to twice the spin. And so we wouldn't expect to get information about a spin 1/2 impurity near the strong coupling fixed point from what we did.
maybe you could make another, if you did a higher order expansion, would you get a correction to this S minus 1/2?
The S minus 1/2 is exact. In more generality, it would be S minus K over 2 for more channels. And in the overscreen regime, it would correspond, you would just have zero coupling, zero remnant impurity spin. Are there any other questions or should I continue?
I'm happy with you continuing, please.
Thank you. Let me go and talk about just the case where K is on the order of S. So our effective action is very similar. The only thing that changes is that our Berry phase contact term gets modified by a factor of K because we have K channels. Unlike in the K equals 1 case, this interaction modifies the pi propagator to leading order in 1/S. And this is exactly where the breakdown in the 1/S expansion for K equals 2S occurs. For K less than 2S and for K bigger than 2S, this pi propagator is still order 1/S, but when K is exactly equal to 2S, this pi propagator becomes order 1 and 1/S. In any case, our beta function gets modified, and our phase shift now becomes a more complicated function of our energy scale. Here, W is a product log or Lambert W function. This beta function here for the multi-channel case agrees with Hao-Yu Hu and Chimiao C's result in 2022. I will point out that they were focused on the K equals 2S or kappa equals 2 regime. And they considered the approach to the perfectly screened fixed point. At the perfectly screened fixed point itself, the 1/S expansion breaks down. However, we were able to study K less than 2S and K bigger than 2S as well, and find interesting results, including the non-Fermi liquid fixed point I mentioned earlier. All right, so that's our RG flow. And with this RG flow, we're able to compute thermodynamic observables. that compare well with the beta ansatz. So here we can just compute directly from the partition function the impurity entropy and also the impurity specific heat, the impurity susceptibility, and the magnetization as a function of magnetic field. And here are some plots comparing how this 1/s expansion converges on the beta ansatz result. So you can see even at s equals 5, we have good convergence between the beta ansatz answer and the large S answer. And here's the susceptibility, and here's the zero temperature magnetization. We are also able to obtain thermodynamic observables for the overscreen regime, the non-Fermi liquid fixed point regime. Here, we get a critical exponent of 2/k at the non-Fermi liquid fixed point, which compares well with the exact answer of 2/k plus 2 for large K and large S. Our value of the impurity entropy at zero temperature also compares well with the exact answer from boundary conformal field theory. And our free energy for the overscreen regime compares well with the beta ansatz free energy. The advantage of our solution, beyond providing an analytic and qualitative way of understanding what happens at intermediate scales, is that we are able to compute observables that are difficult to calculate with the beta ansatz, because we are able to access correlation functions. So one such observable is the impurity spectral function, which tells us the energy states that are available for the impurity electron interaction. And we end up getting the following expressions for the impurity spectral function. In particular, both of these expressions for k equals 1 and in the overscreen regime peak at omega equals 0. So this is the usual Kondo resonance that people have seen in experiments. With the impurity spectral function, we're able to also compute the electrical resistivity. And we end up with the following expression for the impurity resistivity. There aren't any beta ansatz results on the impurity resistivity. There's just boundary conformal field theory results for small temperatures. And our expression compares favorably with the exact BCFT result. Finally, because we have access to correlation functions, we can actually understand, we can actually start to understand the Kondo screening cloud. We can see exactly how this impurity is screened. So the setup for this Kondo screening cloud is to start at t equals 0 in a 3D system with a small bare Kondo coupling rho naught. Electrons away from the impurity will see a screening cloud around the impurity. Very far away, the electrons will see the impurity being screened to either s minus k over 2 or 0. And as electrons get closer to the impurity, they will see partial screening. And one such probe of this screening is a spin correlation function. It's a correlation function between an electronic spin away from the cloud and the impurity spin. It has an oscillating part as well as a uniform part. And we're able to compute the Kondo screening cloud profile just by computing this correlation function in the frozen action, and then using Cal and Szymanczyk to RG improve our expression. And these results agree with perturbative results around the weak and strong coupling fixed point. So I think that gives a good description of what we're able to capture with this new approach to the Kondo problem. Some future directions on the theoretical side that I'll mention are understanding higher dimension spin impurities. There's been a paper by Danu and Grover and others that has considered a chain of magnetic impurities in a metal coupled with an antiferromagnetic coupling amongst themselves. And they arrived at this phase diagram from a Hertzsprung-Millis calculation. And so the question is, can we use a large S expansion which is more controlled than Hertzsprung-Millis to confirm this phase diagram or find a different phase diagram? Another possible direction is looking at quantum quenches, looking at the temporal dynamics of impurity spins. So let's say we start with no coupling between the impurity and this metal, and then we turn on the coupling at t equals 0. And then also I'll mention the comparisons with experiment for the resistivity, impurity resistivity, and other such quantities as another application as well. So in conclusion, we are able to write down an effective action order by order in 1 over S, use it to compute, use our resulting RG flow to compute thermodynamic observables that match beta-Ansatz perturbation theory and past boundary conformal field theory results, and also compute observables that are not easily accessible from beta-Ansatz. Yeah, so that's the talk. Thank you.
Thank you. Any questions?
So does your approach generalize to anisotropic coupling to the magnetic impurity?
So I guess here in the very beginning, we used spherical symmetry to reduce our problem to a 1D problem. And if the coupling is anisotropic, you wouldn't be able to do this reduction. However, it wouldn't stop you from doing a 1 over S expansion. I think it would just make the math harder because now the coupling is anisotropic, so you can't reduce to a 1D problem. But if you're able to do the math for the original 3D problem, then the 1 over S expansion would still hold.
So I know that maybe you're interested in just gaining further insight into this problem, but what do you think would have more application to experiment, like a uniform coupling or a anisotropic coupling?
I think a lot of the experiments I've seen with the Kondo problem and like verifications of it have been able to engineer isotropic couplings. However, in like real materials, I'd assume that you can't assume that the coupling is isotropic. And so there might be some correction due to anisotropy that is worth exploring. And so you could consider higher orders of angular momentum scattering. You could also consider, so I guess here we assume that we had a delta function interaction, but we could, as you said, change the directionality of this interaction and see what happens.
I see. Thank you.
I have a question about the dynamics. You mentioned near the end. Yeah, so
are you talking about the electrical resistivity measurement, or are you talking about the future direction?
Future directions.
Okay. Sorry about this.
All right.
Okay.
Yeah, so how does so what you showed through the most of your talk was, an RG calculation with you wrote down a field theory or something. How
Mhm.
do you study the dynamics? Does large S help?
So what you do have access to from these types of arguments is you have access to correlation functions. And so earlier, I guess this was in the static case, we had access to the spin correlation function from our field theory analysis. And so I think, and like, I'm not entirely sure because I haven't thought through this as carefully as I've thought through the other stuff. But if you were to express the if you were to map this to some action and then compute observables with that action, perhaps some of the formalism that we've used earlier would be helpful. And so like you can write down an action where the phase shift is 0 for time less than 0, and for time bigger than 0, it goes to some rho naught that's much smaller than 1 but bigger than 0, and then measure observables with this new action.
I mention this because I've been interested in, trying to get, like, say you had two of these impurities, can you get them to like entangle with each other or something through the electron gas? Or some kind of quantum information property, which would be something you could access if you could study the dynamics.
Yeah. I think I'm not sure off the top of my head how to put that into our formalism, because now I guess if you put the impurities very close together, then you can, at large enough length scales, you still have spherical symmetry. And so, but at smaller length scales, then you lose the spherical symmetry. And so I'm not sure how important that spherical symmetry is.
Yeah. Yeah. All right.
Other questions? All right, so let's thank the speaker again.
Thank you very much.